Good morning, everyone. In the previous class, we have started discussing the inter-process communication. In that, we have already discussed what two types. That is, one is FIFOs, and the another one is the named FIFOs. The named FIFO is nothing but the process which are unrelated, whose parents they don't have a common ancestors. There, if the process has to communicate, then they are going to use named pipes, or they have to use just the pipes. And we have discussed the advantages where they are going to use. In the client server communication, they are going to use the this named pipes. And I have told you that in your network lab, there is a program on named pipes. That is the best example where you can see, we can see the FIFOs. The next topic is XSI PC. Means there are another three types of inter-process communication. Till now we have seen the FIFOs and the pipes. The next are the one more the three types of inter-process communication IPC types. They are going to call this as a XSI IPCs. They are all the in that the three IPC types are: one is the message queues, the second one is the semaphores, another one is the shared memory. We are going to discuss these inter-process communication types one by one. Before we start the message queues, some background about these three we are going to discuss now. What is this? The second category. This till now we have seen the named pipes and just the pipes. Why this is and another? Why these are required, or how we are going to use this the message queues, and is there any advantage is there compared to the previous named pipes? That we will discuss now. See, this XSI IPC structure, XSI IPC structure, if I use the word XSI IPC structure or IPC structure means these three will come: message queue, semaphore, or the shared memory. What will be the structure in the system? How we are going to identify in the system? If you say, then it is being uh, identified with the number sub integer. It's a non-negative integer identifier. It is been identified with the non-negative integer identifier. There will be a internal name and there will be an external name. In the system, if you check, it is with the internal name will be the number. That number is non-negative integer identifier. Whenever you create this IPC structure, create is nothing but whenever you create a message queue, or whenever you create a semaphore, or whenever you create a shared memory. Why you need to create these things? Because you want to perform the inter-process communication. Two process has to communicate. Then the two process which they want to communicate, they will create a message queues and they will communicate, or they will create a semaphores and then they will communicate, or with the shared memory they are going to communicate. That whenever they create, they are going to call it as an IPC object. Whenever they create this IPC structure, we are going to call it as an IPC object. That object contains two things. What it contains? It contains identifier and the key. Two things it contains. Who will give the key? As a user, when I create this IPC structure, I have to give key as a parameter. There are functions to create. In order to create a message queue, MSG get is a function. To that parameter have to pass one value will be key, second value will be flag. Two values we are going to pass it as an argument. That we'll see the in detail about that API next. As of now, you just remember message queue get is a function. For that, you are going to give a key. That key data type is key underscore t. It is almost a long integer data type. It is a primitive data type. It is a long integer. That key, whenever we create or whenever you open a message queue or a IPC structure, you have to pass. Whatever we give, that is called as a key. That key is called as an external name. For internal control operations, the operating system is going to operate the message queues or operate the semaphores or operate the shared memory with the unique identifier that is a number. It's a non-negative integer identifier. That is an internal name. I think now it is clear. External key value we has to specify, and the function whenever we create, the return type will be from that function is msg, that message queue. Whenever we create, the return value will be a integer. It is a very big number. It is not small number. It's a very big number. Whenever we continuously use it, that number is going to increment. It reaches some maximum value. It may start from 1, 2, 3. That number, it may increase and it may reach some maximum value, and once again it will wrap around till 0. The conversion from key to that identifier, non-negative integer identifier, that will be done by the kernel. See, we'll call with that just function. We'll pass two parameters. One will be the flag, another one will be the key value. Internally, the kernel will use that key value and it will return you the unique identifier. That is what it will be done by the kernel, converting a key value to an identifier, an internal identifier. Now, in the system, any message queue is identified with the number. It can be any number of message queues, but it is identified with the number. How to create the keys is the next question. See, in the client server communication, we for client server communication, we require any of the IPC type. It can be the named pipes, FIFOs, or these things. Which one, the message queues, the semaphores, or the shared memory. Here, keys are required. As I already said, we have to pass the first parameter called key. There are three ways. In the client server communication, what happens is the server itself, now the server has to communicate with the client. The server itself is going to create a key and it will store it in a file where the client is going to read. From that file. The server will create one key and it will create an IPC structure. Means whenever it creates an IPC structure message queue, from that function, it is going to return you the non-negative integer. I'll show at first message queue, and this is the function int message get key dot flag. The return type is int. This will return you the message queue ID. This will return you the message queue ID, and this is in the same way you have it for semaphores and also for the shared memory. Now I think this is clear. This is going to return you this integer. In this way, the server is going to generate the IPC structure, that is message queue or any other things, and whatever the return internal integer, that will be shared with the client. How? It will store it in a file where the client is going to read. Then what the client will do, it will open that file. Now that number will be there. Once again, it is uses the same function, message get. There it is going to pass the that queue ID and it is going to communicate. Whatever the client wants to send a message, it will add it to the queue. The server, it will read it from the queue. Once again, the server wants to send anything, it will add it to the queue. The client will read from that queue. That's all. The second way is the client and server both is going to agree for some key. It's a random key. Both will agree for some key, 1233. They are going to agree and they'll start using. The problem with this method is if that key is already been assigned for another IPC structure, you have already created in the system, if that that number is been, that key has been assigned for the other, then error handling will be should be taken care. It will throw the error because you cannot give the same names to the multiple IPC structure. Two message queues cannot have the same number, 1100. It should be a different number. In that case, we are going to delete that IPC structure and once again we are going to call. So that is a second way of creating a key. The third way is there is a function called FTOK. That function we are going to use and generate the key. That function we are going to, that function to the key. That function we are going to use it to generate the key. For that, what we are the parameters we are going to pass is some project ID, that number from 0 to 255, any number. The second parameter is 0 to 255. That number we are going to give, and it's a path address of an existing file that we are going to give. Then that function FTOK function, it will take these two parameters and it will generate some key. That FTK function, it will generate some key, then that will be used by the client and server. Both they are going to use that same ID. That same ID. In three ways, you can create the keys. One will be server will create, the client will use. Second one, both will share the same key, they will agree, but there is a problem is there is a chances of already that number being used by the other IPC structure. If I use the word IPC structure means message queue, shared memory, semaphores. The third case is the client and servers will agree on the path name and the project ID and they will give it to the FTK function and that function will generate the key. This is the another way. Then say in the background, whenever we create the IPC structure, some more information is being assigned automatically and it is stored at one place. For our highs, whenever we create, it is going to return a some number. But in the background, it is going to assign some values and stores at some place. What it stores is there is a structure, IPC structure. In that IPC structure, it is going to store some values. There is a structure called IPC underscore permission. This structure we are not going to create as a user. The message get function, that message queue function, automatically it is going to set. What all the fields it is going to set? Owner's effective user ID, owner's group ID, creators user ID, the file permissions, everything is being stored in that structure. And this structure, it is for one IPC structure. If you create one message queue, one structure will be stored with all these values. And if you create one more message queue, all these values will be stored. It is nothing but it is just, it is going to store who has created all these things and what are the permissions that will be given on that IPC on the message queue. That is called as a mode. That is called as a mode. All these fields are initialized. As a programmer, we are not going to initialize. That will be initialized automatically. Here, they're going to give all the permission except the execute permission. In that mode option is there, right? Mode, the last parameter, that will be, it is same as the open function, but where the execute permission will not be set. Only the creator of this IPC or the root can change this. Hmm? Who has created the message queue? This person only can change the permission, all those things, that IPC structure. How it is going to check? Whether I have created or you have created, all that informations that will be stored in that structure. Whenever you log in, there will be a login ID, right? From that ID, it is going to check in the structure whether the same user is using this structure, and then it is going to allow. And in this IPC structure, they have a built-in limits. The number, how we are going to use the message queue has a built-in limit, semaphores has a built-in limits. There is some limitations, and also those limitations you can change by reconfiguring the kernel. If you reconfigure in the kernel, you can change it. What all those limitations? Those limitations we will discuss with one by one when we discuss the message queues, when we discuss the semaphore, and when we discuss the uh, shared memory. Totally, what is an advantages with this IPCs, these three IPCs? What are all the advantages and what are all the disadvantages? Compared to the previous named five FIFOs, what are all the disadvantages with this IPC structure, message queues, say shared memory and semaphore, or what are the advantages? The problem here is, the main problem is, these IPC structures are system wide, means whenever you create the message queues, it will be inside the operating system itself. Until you delete it manually using those functions, it is not going to be deleted. That is why they say it is system wide and they do not have a reference count. They do not have a reference count. Programmatically, you have to delete those IPCs. The another problem with this IPCs is these structures are not known by the names. They don't have a names. How to identify in the system? They are with the numbers. If they have with these numbers, you cannot, it is easy to modify their properties. If you want to change any settings, you cannot easily modify. Change the properties is nothing but you cannot use ch mode, you cannot change the file permissions. That is the problem. If you don't have a name with these numbers 1445, with those unique identifiers, you cannot change the properties. That is another problem with these IPC structures. And also, there is one more problem with this IPC structure is, since they don't have the file descriptors, with these numbers, you cannot use more than one IPC structure at a time, multi-programming. Multiple IPC structures you cannot use at the same time. That is why you cannot perform the operations on the device input output. One by one, if you do, it consumes more time. That is also a problem. But what is an advantage? But it is reliable. You can control the flow, and all the informations are being getting stored. It is not going to miss anything. You can depend on this, reliable. But these are the still the disadvantages are there with this message queues, shared memories, and semaphores. Now we'll discuss one by one message queue, semaphore, and the shared memory. What is this message queue? The message queue is nothing but it's a queue. A simple queue, whatever you have seen the stack and the queue, it's a queue where the data will enter from one end and it will be removed from the other end. And what it contains in the queue, it is the messages. It is a linked list of messages. Even here, the messages may be retrieved out of orders. It is not the first message in the queue you have to take out. The messages may be retrieved out of order. You can take any message or you can delete any message. Similar to the FIFOs, it allows the two or more processes to exchange the data. If two processes want to communicate, then they will suddenly create the message queue and they will exchange the data. How they will exchange the data? In that queue they are going to add, one process will add and the other process will take it. The message queues remains until deleted or system rebooted. This is the problem which I have told. Until you manually delete it or the system reboots, it will present in the system memory. It is going to present in the system memory. See, this is a queue and in the out of order, you can retrieve it. How it is possible? Because they have been stored with the linked list and with that linked list, you can easily get the messages. And these messages, each message, it will have its own identifier. Each messages also, the message queue as an identifier and each message queue as its own identifier. Whether the values which the messages within the queue which presents, right, whether it should be of similar type, no, it can be of different types. And the message function that we are going to use here to open the queue or to create the queue is message get. To add a message into the queue, we are going to use the function called message send. In order to fetch the messages from the message queue, we are going to use the function called message receive, MSG receive. We'll see the structure, the functions one by one. We'll see the structure one by one. See, whenever the new queue is created, whenever the new message queue is created, in the background, as I already said, the data structure will be set. A data structure will be set in the same way. Here for the message queue, there is a structure. For a message queue, there is a separate structure. For a semaphores, there is a separate structure. For shared memory, there is a separate structure. These values will be automatically being initialized. The structure will be, it will already be there and it will be initialized. And this data structure, it will be associated with the each message queue. What it gives information? It gives the information about the current status of the queue. When it has been created, what is the PID of the last message sent, which message has sent the message. Some process has is going to send, right? Some process is going to get the message from the queue. Their IDs, process IDs, that will be stored in this structure. How many number of messages are there in the queue? All those informations will be stored in this queue. As a programmer, we are not going to set it. Automatically, it's getting updated in the background. This is a structure, message, QID, data structure. This is going to be associated with the message queue. Now we'll see the function one by one. See, first one, to create a message queue, the function we are going to use is msg get, where actually it is going to be found in the header file sys.message.h, and the key is in the system sys slash types.h. In that, the key underscore t data type is going to be present. What are all the parameters? Two arguments that you have to pass. One will be the key, the second one will be the flag. The flag is it completely about the permission. The flag is about the permission structure, and we have to pass these two parameters, and it is going to return you the message queue ID, some ID. It's an identifier. If something is, if it fails in creation, then it will give you the -1 error. It will give you the -1 error on -1 on failure of creating the message queue. The second function is message send, MSG send is send. This message send, now the queue is ready. Now some process has to add their information into the queue. Then they will call this function. If they want to call this function, some unique identifier is there. That number is the first argument, int message queue ID. Then only it will go and sit in that particular message queue. What will be the second parameter? Some pointer. What is that pointer? Is the pointer, it is going to point to some location where exactly the message is there. That message will only go into the queue. That is the address. That pointer is shows the address where message exactly it presents. From there, the data will be copied. What is the size? How much message is there? That will be indicated in terms of bytes. That will be the third parameter, n bytes. The fourth one will be the file permissions, the flag. That will be the flag. Now it is clear. Message queue ID, it is an internal ID of the queue. The second one will be the address where exactly the message is there. What is the size of that message in terms of the bytes? And lastly, it is the flag. If that is the one case, the next one to receive. You have sent the message. In order to receive the message from the queue, then you have to pass these parameters, these many parameters. First one, from which queue you are going to receive message queue ID. That is the unique identifier. Second one, where exactly you are going to copy that message which is retrieved from the queue. The message, whenever you copy from the queue, it has to be copied to some location. That address, that address will be, that pointer will be the second parameter. And how much size it can hold, that message size it can hold, that will be the third parameter, n bytes. That is a text portion of the structure pointed out by the pointer. That is about the size and the message. Then the other two parameter is type and the flag. See, the longed type is which message you want in the queue, whether it is a first message, whether it is a second message, third message, that is that will be indicated by the type. If you give the type value as 0, if you give the type value as 0, the first message of the queue will be returned. If you give any other number greater than 0, that which is going to match with the queue number, that will be returned. Even if you give the type less than 0, the first message of the queue will be returned. The first message on the queue will be returned. That will be the type argument. Now I think it is clear. Type argument, it is which message you want in the queue, that you have to specify as the fourth parameter. Once again, the permissions, the flag. You have another function that you can operate with the message queue is some control operations. Some control operations on the message queue, the various operations that you can do on the message queue is, see, if you want to delete the message queue, then that we are going to call it as an operation. The various operations that you can do on the message queues is this. See, that is done by the function called MSG control. Which are the parameters? MSG that is the which on which message queue want to operate. The second one is command and some structure. What is this command argument is? What is the operation you want to do on that? That is the main thing. See, that first option, what is the operations you can do is IPC underscore stat. If you gave the command number, the second argument as IPC stat, and then what it is going to do is, say in the background, there will be a data structure, right? For each queue, there will be a data structure. That data structure, fetch the data structure for this queue. That data structure will be fetched. Fetched is nothing but to where it is going to copy. It is going to copy to this star buffer. See, message queue ID underscore data structure star buffer is there, right? This star buffer, this buffer entirely, it will get a copy of the particular message queue ID. Whenever it is been created, that so much information is there, right? That entire structure, it will be copied to this. In that case, you want to give the second parameter as IPC underscore stat. If you want to copy whatever it is there in the parameter into uh, the existing structure, for the existing structure you want to copy from here, the new values you want to copy. In that case, IPC underscore set you have to use. Whenever you do that, then whatever the fields that BUF buffer which is going to point, those values that will be copied to the existing data structure. It is keeping the backup. Or you are going to change the values which is already been existed. If you want to change that with the new values, the third parameter, whatever you pass here, this data structure, that is going to copy to the existing data structure. The existing data structure you want to copy to this buffer, then the command should be IPC underscore stat. Set means copy. Then IPC underscore RMID if you use means now you want to, from the system, you want to remove the message queue from the system. Then you have to pass the parameter argument as IPC underscore RMID that you have to pass. Quickly it is going to remove that message. Any data which is going to be present, that is going to be deleted first of all. This is a control operation. The next thing is semaphores. That we're going to discuss the semaphore in the next session. Till now we have discussed the three types, the XSI, IPC, message queue, semaphores, and the shared memory. Some background we have discussed. These three IPC structure, they are going to be identified with the non-negative integer itself. There will be a key, there will be identifier. One is called as an internal name, another one is an external name. This is called as an IPC object. And what are the advantages with this? What are the disadvantages with this? And we have started with the message queues, and with the message queues, uh, how we are going to create, what are all the queues, what is the queue, whether we how they are going to store, whether it is a linked list or not, whether we retrieve in the out of order, then which are the functions we are going to use to create or to open the message queue, msg get, to send which function we are going to use, which function we are going to use it for receive the message, where exactly they are going to store, and control operations, which one we are going to use. Everything we have discussed. Now we are going to discuss the semaphore in the next session. Thank you.